second law? Well, we already know that when a planet is farther from the sun, there's less pull of gravity, and so it has a slower velocity. But when the planet is closer to the sun, it has a stronger pull of gravity, and it has a faster velocity. Kepler's second law of motion digs even deeper into understanding what that velocity means for the planet's orbit. So Kepler studied orbits and figured out that the area a planet is sweeping in its orbit. So you have an imaginary line. If our planet is here, we have an imaginary line between that planet and the sun, and that will be the same for any two equal time periods. So you can see here that we have from P1 and P2 and P3 and P4. Oops, I put the P backwards over there. So from P1 to P2, it takes the planet 152 days to travel this distance. But it also takes the planet 152 days to travel this distance. So we see those being the same time because they have the same area. So we're using that imaginary line. The planet sweeps out the same area in its orbit. So for question number 1 on that Google form, what does Kepler's second law tell us about a planet's orbit? Please pause the video and respond to number 1 on the form. When you're ready, start the video again. We can use this image and animation to help us see that Kepler's second law, the law of equal areas, has some interesting information that we have to look at. So we've already talked about the speed and what Kepler's second law says. So we can see here that this planet is traveling around the sun, and you see those gray sections of the orbit are highlighted. Well, if I know that all of those gray areas have the same measurements and the same area, I know that when the planet is going from here to here, it's going to take the same amount of time as when it's going from here to here, from here to here, here to here, and all the way around the orbit. It's going to take the planet the same amount of time to cover that same amount of space. Now you might notice that some of these slices, like our pizza, have a longer edge, more crust, if you will, and others are smaller. That's where the velocity comes into play. We're looking at the same amount of time, but sometimes the planet is going to be going faster, and sometimes it's going to be going slower. So if the distance it's traveling in the orbit, the section of the orbit might look smaller, but the total area is the same. So even though the crust might be a little bit bigger or smaller, the time is what we're looking at, and the time is the same, so the area is the same as well. So here we have some data to help us see that law of equal areas. You can see the planet is traveling from A to B, all the way around, and then C to D, and it's traveling in its orbit. It will take this planet 24 days to travel from A to B, and 24 days to travel from C to D. So what pattern do you see? In the data table, we see the area and the time of travel. What pattern do you see in the area and time of travel? Please pause the video and respond to question number 2 on the form. Now we have to think about what if we only know one piece of information. In question number 2, you knew both the area and the time. In this diagram, we see that it tells us the blue areas are equal. But what information could we use to know that for sure? Well, we could measure them and calculate it, but it's actually a little bit more complicated than calculating the area of a triangle like we did with the pizza. So how else could we know the blue areas are equal? Please pause the video and respond to number 3 on the form. So what we have seen so far is that if equal areas are swept over the same amount of time, so this area here that I've shaded is equal to this area here because the time is the same. So if equal areas are swept over the same amount of time, the shorter the arc, we can see here, the arc is the section of the orbit that we're looking at, the crust, and then we see with the shorter the arc, the slower the speed. And we know that makes sense because the planet should be traveling slower when it's farther away from the sun. But the longer the arc, the faster the speed. So the planet's going faster when it's closer to the sun, so it's going to cover more of the orbit, but the area of space is going to be the same size. So here we have another diagram, and I want you to think about what can you conclude about the area of section 1 and section 3. Please pause the video and respond to number 4 on the form. Now let's look at some data. How long will it take to travel from T3 to T4? So notice we have a data table here. We have T1 to T2, T3 to T4. We see their areas and we see the time of travel, but we're missing how long for T3 to T4. So how long will it take to travel from T3 to T4? And how do you know? Please pause the video and respond to number 5 on the form. Now we're looking at a little bit more complicated diagram. Please identify the missing values in the data table. You can see they're highlighted here and here. Use your knowledge of Kepler's second law. This is the law of equal areas based on what you see in the data table. Please identify those missing values. So we're looking for the area from points 2 to 3, and we're looking for the time of travel from points 6 to 7. Please pause the video and respond to number 6 on the form. So in conclusion, Kepler's second law tells us a lot about the planet's orbit. Any planet covers the same area in equal periods of time. So if we were to look at the Earth traveling around the sun, in 30 days, anywhere in the orbit, from day 1 to day 30, that planet is covering the same area because of those equal time periods. Please be sure to submit the form when you're finished and let your teacher know so that you can complete a retake. Thanks for watching.